It's Prof from the University of Nairobi. This is our third video on approximate integration. You will be looking at the concept of Simpson's rule. Okay, so we'll be talking of Simpson's rule of approximating integrals or the area of curves. Okay, so we'll be talking of Simpson's rule, how to calculating the area of curves using the Simpson's rule. So I'll just write the formula. So Simpson derived a formula for calculating the area of curves. We can derive it, but for time and easiness, we just write the formula, show how to maneuver through the formula, and we'll be cool. So the area is given as delta. Okay, in my last 3 videos we have shown how to calculate delta divided by 3 into, okay, y0, y0 plus, from here we just have to alternate 4 and 2. So I will just say, we usually start with 4. So I usually say 4 y1 plus 2 y2 plus 4 y3 plus 2 y3 4. Okay, so we just alternate. Look here, we just alternate 4 and 2, 4 and 2. Okay, and the process continues till we get 4 to the y of n minus 1, okay, plus y to the n. So this is our formula. That's how we compute that. So this is the area approximate using Simpson's rule. This is the formula. So straight away I'll just write an example. For example, evaluate the area given by the integral of x squared, okay, dx with n equals to 5 from 0 to 10. Okay, the values of n is 5 from 0 to 10. So straight away try and picture the graph, the way the graph looks like. So just try to picture the graph. The graph will look like that. The y-axis, the x-axis. So the graph looks like that. It's just a U-curve that has opened up. Something like that. So it's from 0 to 10, for example. So the area we are required to approximate is this. Okay, this is the area we are allowed to we are required to approximate. And just an explanation for this: Simpson's rule, it's more accurate than all the previous 2 rules we have talking about, midpoint and the trapezoidal rule. So from here, we'll just again calculate our delta x. So let's compute our delta x. Delta x is the same as from 10, okay, from 10 minus 0, that is just 10, divided by 5, n, the value of n. So our delta x again is just 2. Okay, so our delta x, let me write here, this our delta x, just for familiarization. Our delta x again is 2. Okay, so let's calculate our y0, y1, y, and so on and so on. So from there, we just draw an x-axis that usually say draw just a number line, but it's just an x-axis. So draw an x-axis. Okay. Drawing an x-axis to be that. Drawing an x-axis. So our delta x is 2, and we said that is the interval of the triangles of the rectangles we are trying to make. So it's from 0, then the interval is to 2, then to 4, then to 6, then to 8, then to 10. It's simple. Okay. So it's that way. It's just, okay, Simpson's rule is just the same as trapezoidal rule. The change is divided by 3 and alternating 4, 2, 4, 2, 4, 2, and so on. So that's just the difference, but everything else similar. So from there, let's just compute our values of y. Okay, so let's say our y0. Our y0 is where x equals to 0. The value of x is just the x-axis. So our y0 is where x equals to 0, and we say this is just the function. The function is y equals to x squared. Okay, just replace that. So our y0 is where x equals to 0, it will be 0 squared. 0 squared is just 0. Our y1 will be where the value of x is 2. So it will be 2 squared equals to 4. Okay? Our y2 is where the value of x is 4, so it will be 4 squared is just 16. Y3 again, similar, we said 6 squared equals to 6 multiplied by 6, that is 6, sorry, I almost forgot that. Y to the 4th is where the value of x is 8 squared, so it will be 64. Okay, where y, sorry. Y to the 5 equals to where 10 squared equals to 100. So these are values of y. So just let us just replace back the formula. Let's compute our area. So I'll just clear all these. Just clear that. Having the question in mind. Having this value, so I'll say my approximate area. Okay, my approximate area will be delta x. We said that delta x is 2 over 3 into our y1 is 0, so it's 0 plus 4 multiplied by our y1 is 4, okay, plus 2 multiplied by 16, right, plus 4 multiplied by 36, okay, plus 4, so we continue to 2, plus 2 multiplied by 64, plus now, so this is the last term. We don't usually alternate the 2 and the 4, so the last term is independent, just the same as the first term, so it just be 100, as simple as that. So let's just complete. So our area will be 2 over 3 into, let me add that. So it will be 4 and 4, 16, 32. This is 4. 144, right? This one 58. So it will be 16. So doing these computations, you get 420, so it will be 420 multiplied by 2 over 3. 420 multiplied by 2 over 3. You get answer as 280 square units. Okay, let's find our exact area again. So this is our area, so let's calculate the exact area. The exact area, back, we calculate the exact area using, the interval changed, the interval was different. So it will be the area, okay, equals to the integral of x squared from 0 to 10. Okay, so just 1 over 3 x cubed from 0 to 10. So we'll just get 1 over 3 multiplied by 10 cubed. So just placing x with 0 will just be 0. So just 1000 divided by 3. We get our area as 333.1 over 3. This is our answer. Okay? So, we have found an error. We have an error here. So the exact area is 303 square units, but our approximate area is 280 square units. So having this concept, we just calculate error bounds. The error bound, as we said in the previous videos, we said the error bound and the maximum. Okay, the error bound is the maximum error that you are allowed to create. Okay, you are allowed to create while computing approximate integration. So our error bound by Simpson's rule. We have the formula error. We have the formula error given by the Simpson's rule. It will be error, okay? Error created by the Simpson's rule. Simpson's, sorry, this is a small s. Absolute value. It's less or equal to, okay? K, the same formula, K into B minus A, but now this time we raise it to the power 5 instead of power of 3. So just raise it to the power 5 divided by, okay, 180 multiplied by n to the 4th. So this is how we calculate the error bound using Simpson's rule. So we said the error from 280, so let's calculate the error that we have created. Let's calculate the area, sorry. So let's calculate the area at first, then we'll calculate the error, the maximum error or the upper bound error that we are allowed to find. So the error we have created must be less than what we get here. So the error will be this minus 280. The error we are allowed to create, okay, the error that we have created, the error that we have created is 53 and a third. This is the error we have created, okay? And when finding this error, this is the maximum error that we will be allowed to create. So it will be less or equal to our k again. Let's find our k. For this case, we'll find our k as the 4th derivative. Okay? Just right. This is the error we have created. Remember, we have created this error. So k. How will you find our k? So our k is found by the absolute value. Okay, the absolute value of the 4th derivative of x, okay, less or equal to k. This is how we find our k. It's different from midpoint and Simpson's. Midpoint and Simpson's, here it's 2nd derivative, here it will be 4th derivative. So let's find our y. Our y equals to x squared, okay? Y is equals to x squared. So we'll just write, this example is funny, but it will just suffice. So our first y, okay, will be 2x. Our second y will be just 2. Our third y will be just 0. Our fourth y will be 0 again. Interesting. Okay? So my value of k will be just 0. My k will be 0. That's my value of k. According to this example, remember? According to the example, my value of k will be 0. Okay? So, okay? This example is kind of weird. My error is supposed to be 0. Example, it's weird. Okay? But the concept is the same. So I just get my value of k as 0. So it will be 0. Let me write it will be 0 into what's b, that is 10 to the 5th, divided by 180, multiplied by n to the 4th, where n, we said n is 5, so it will be 5. All this is just 0, because 0 divided by any number is okay. So the example is the example is weird though, but the concept is that's the concept we require. So the maximum error I'm required to create is 0. But according to Simpson's, okay, the error that we have created is 53 and a third. Okay, the example itself was wrong, but the same procedure applies. Fourth derivative of absolute value is the same as k. That way, so we just compute that. So this is how we handle the error bounds in approximate integrals. My next video will just talk of an example, sample question from the University of Nairobi, dealing with the midpoint rule. And I have an example dealing with the midpoint rule. We'll talk of that. We are told the last question I think was finding the maximum values of n such that the area of approximation will be 0.0001. We'll talk of that. Thank you. Don't forget to like, share, and subscribe. Thank you.